Hw9 Q2. Here we're presented with a volume and a molarity for each of two reactants. Automatically I know that this is going to be a limiting reagents problem because they're giving us enough information to find moles for two things. Part of the challenge, of course, is to convert between words and formulas. So we know that barium sulfate is going to be the precipitate, and we've got two reactants, barium chloride and iron 3 sulfate. So think back to your nomenclature, and we can write an equation for this. Iron 3 sulfate would combine with sulfate in a 2:3 ratio. To write the products, well, they gave you a hint in telling you that barium sulfate is going to precipitate, but you could also just say, what are the new combinations of ions that we could form? The other product besides barium sulfate would be iron 3 chloride. By solubility rule 4, you would say, oh, sulfate salts are soluble except for, and if you look carefully under the exceptions, barium sulfate is an exception. Solubility rule 3 would tell you that chloride salts are soluble. And, of course, automatically reactants are aqueous. This does need some coefficients to make it balance. We need a 3 in front of barium chloride, a 2 in front of iron 3 chloride, and a 3 in front of barium sulfate. And let's record the information they gave us. They tell us for both of the reactants a volume and a molarity. And in my case, the red numbers are the same. So 500 milliliters of 0.1 molar and 500 milliliters of 0.1 molar. From that, we'll calculate numbers of moles. For an easy, quick comparison, you could just keep the volume in milliliters and multiply straight across. So 500 times 0.1, or 1/10 of 500, you can do this in your head, is 50 millimoles of the iron 3 sulfate. And we also have on hand 50 millimoles of the barium chloride. Now, we can make, conveniently, since the number of millimoles is the same, we can say, all right, one of the reactants has a coefficient 3, and the other reactant has an implied coefficient 1. So the reactant that has the higher coefficient is going to get used up quickly, more quickly than the other. So we've identified the limiting reagent without having to do its own set of calculations. We know that barium chloride will be limiting because it gets used up 3 times as quickly as iron 3 sulfate does. And given that there's the same number of moles of each reactant, that means that the barium chloride will run out first. Okay, 50 millimoles is the same as, if we convert that back into moles, 0.05 moles. So we're going to do a little stoichiometry. The problem asks us to find the mass of the precipitate barium sulfate that is formed. So we're going to convert from barium chloride to barium sulfate. Notice that the coefficient for both of those species is 3. There's a 3 coefficient for barium chloride, shown here, and a 3 coefficient for barium sulfate, shown here. And if we multiply through, one last thing, since they want mass, let's add another conversion factor to this, keep everything quick. For every 1 mole of barium sulfate, you would then look up the atomic weight of barium, of a sulfur atom, and of 4 oxygen atoms and add them together. It works out to be 233.4 grams for every 1 mole of barium sulfate. Then, as you can see, the moles of barium chloride crosses out moles of barium sulfate crosses out, and grams of barium sulfate is the unit left over, which is what we'd like. So on my calculator, we're just going to type in 0.05 times 3 over 3, which is the same as 1, times 233, and it works out to be 11.7 grams of barium sulfate.